Now let's learn the Kirchhoff's current law and the Kirchhoff's voltage law. So hereafter, when we are applying Kirchhoff current law, we use the abbreviation KCL, and when we are using the Kirchhoff voltage law, we use the abbreviation KVL. Kirchhoff's current law says the algebraic sum of the currents entering a node is zero. That means whatever the current coming into the node is equals to the current going out from the node. So if you look at this example, you can see I1 is coming in and I3 is coming in and I4 is coming in. So when you add these three together, that will be equal to whatever the current going out, which is I4, I5 and I2. So we can say I1 plus I2 plus I4 is equals to I2 plus I5. Let's do two examples with the Kirchhoff current law. So let's start with the first example. So you can see we have a current source, we have resistors R1, R2, R3. We don't need to know the values of the resistance. So you can see 8 amps coming into this node and 2 amps going out and I is going out. So if you look at the currents coming into this node, it is 8 and it should be equals to the current sum of the currents going out from the node. So that should be 2 plus I. So we can find I should be 6 amps. So 8 coming into this node, 2 going to the left and 6 going to the right. Let's look at the other question now. So again, we have a current source with 8 amps and we have 3 resistors in parallel. So this current 8 amp is coming to this particular node and it is splitting. So 2 going this way. So 8 coming in, 2 going this way, 3 going this way. The remaining should go at the top branch. So 8 should be equals to 2 plus 3 plus I1. So I1 should be equals to 8 minus 5, which is 3 amps. Kirchhoff's voltage law says the algebraic sum of all the voltages around a closed path, which is a loop, is 0. So that means the algebraic sum of the voltages is equals to 0. Now let's see how we can apply this. So when you have a circuit, so this is a closed path, loop. So you can start at a point and you are going to add all the voltages around this loop. So they have given us the direction of the current. So let's go in the direction of the current and we add all the voltages. So we start at, this is our start. So we start at a point and we are going to a voltage source here. When it is entering the negative side of the voltage source, we consider it as a negative. So negative V1. Then it is going to the resistor. So resistor is a consuming energy element which is consuming energy. So always the current is going into the positive side and going out from the negative side. As we discussed earlier, in a voltage source, it is supplying energy. So the current is going out from the positive side. So here, when the current is going into a positive side, then we add it. So V2. Then again it is going to the positive side of V3, so V3, and going to the negative side, so it is a negative V4, going to the positive side of V5 and going to the start point. So this is a closed loop and this should be equals to 0. So we can write this equation. This is the algebraic sum of the voltages around a loop and that should be equals to 0. So as I have explained you before, whenever the current is going to the positive side, that voltage is a positive voltage, and when the current is going into the negative side of anything, it can be like, it can be any element. When the current is going into the negative side, we consider it as a negative voltage. So we have to do it correctly, otherwise we can go wrong when we are applying the KVL. So when the current is going into the positive side, it is a positive voltage. When the current is going into a negative side, it is a negative voltage. So here V2 is positive, V5 is negative. So when you are adding, you need to take the algebraic sum. So you need to consider this sign convention. Let's do some examples. So I'm going to apply the KVL to this loop. So I'm starting at a point. You can start at any point, it doesn't matter. So I'm starting at this point and going into the positive side. So this is a positive V1. Then I'm going into the positive side of 2 volts, and I'm going to the negative side of the voltage source, which is negative 12, is equals to 0. So they're asking us to find this V1. So we have an equation. So V1 plus 2 minus 12 is equals to 0. So V1 minus 10 is equals to 0. So V1 should be 10 volts. So we can find the V1. We have another example here. Again, I'm starting at a point. Can be any point. I'm going into plus 8 and then negative 20, then plus V1 plus 2 minus 4 is equals to 0, because I'm coming back to the start point. So we have 20 plus 2, 20 minus 8 and 2 are plus, so that will be V1 minus 14 is equals to 0. Is that right? So negative 20, 24, you are minus, yes, so that is equals to 0. So V1 is equals to 14 volts. Another example, start at a point. So we can say plus V3 and minus VA plus V1. Here, even though we have a voltage source, current is going into the positive side. We are considering the clockwise direction. Current is going in the clockwise direction. So we need to say it as plus VB and coming to the positive side. So plus V2 is equals to 0. But in the question, they are asking us to find an equation with current I. So you can see here, we can write an equation for these resistors considering the current, voltage and the resistance using the Ohm's law. So you can say here V2 is equals to I times R2. So you can substitute this one in V2. Similarly here V3 is equals to I times R3. Here V1 is equals to I times R1. So we can substitute those values, and we can first let's consider V1 plus V2 plus V3. I'm simplifying this, is equals to, you can say, VA minus VB. I'm just simplified this one. So instead of V1, you can write IR1, and instead of V2, we can write IR2, and we can write IR3 is equals to VA minus VB. Now I is common, so I'm taking the I out. So we can say R1 plus R2 plus R3 is equals to VA minus VB. So we can say I is equals to VA minus VB divided by R1 plus R2 plus R3. So we solved it using the Kirchhoff voltage law. Here we are going to use both the KCL and KVL to find I1 and I2. So let's see here. If you apply the KCL, you can see when you consider this node, 2 amps is coming here, and I2 going this way, and I1 coming into this way. So if you apply the KCL to this particular node, you can say 2 and I1 coming in and I2 going out. Whatever the current coming in should be equal to the current going out. So we have one equation here. Now if you write this I1 and I2 or else we can apply the KCL to this loop 1. So I'm going to apply the KVL to this one. So you start at a point and you're going around the loop. So we have minus 20, and here when it comes to this one, it's a positive, and the voltage across this resistor, voltage is the current times the resistance. So I can write as 5I1. Current is I1, the resistance is 5. So it is positive, and it is going to here again plus, it is 5I2. And I'm coming back to the start point, so this is equals to 0. So we can simplify this one. We can say I1 plus I2 is equals to 4. I divided each term by 5, and I took the 20 to the other side. So this is my second equation. So you can see now we have two simultaneous equations. By solving these two, we can find the I1 and I2. That's the question. So we can consider one, and I'm substituting from I2. Substitute I2 using the equation 1. So I can say I1 plus, instead of I2, I'm going to write 2 plus I1 is equals to 4. So I can say 2I1 is equals to 2. So I1 is 1 amp. So I'm substituting I1 here. 2 plus 1 is equals to I2. So I2 should be 3 amps. So we found I1 and I2 using the KCL and KVL. There are different methods that we can use to solve this, but we did it using the KCL and KVL.